Last time we considered rational Rosinar's Schneider model. The most general version of this model is elliptic, when the dependence on coordinates is elliptic. And the Hamiltonian is as follows. Where sigma is the Weierstrass sigma function. The equations of motion, it's a problem for you to derive equations, Newtonian equations of motion from this Hamiltonian. And the result is as follows. Where zeta is the Weierstrass zeta function.
If this h plus or h minus,
What?
it's not the general Newtonian, but for positive or negative time, no?
It's for positive time, but for negative time flow, the equation is the same. When you write here minus, here, so it can be checked that you see that this equation is the same for eta and minus eta. And it can be checked that this coefficient here can be arbitrary. But this, the equation depends on this coefficient, but here we have plus minus, so the equation remains the same. Equals 0. It can be written using some identities for Weierstrass functions. It can be elliptic. It can be written in the following way: equivalent. This model has a lax representation in terms of this function phi of x lambda, Lamé-Hermite function. The lax matrix is M matrix is as follows. the problem is to prove that the Lux equation with these matrices is equivalent to the equations of motion. From this Hamiltonian, you can find velocities. And see that trace of this Lux matrix is proportional to sum of all velocities. But taking into account this formula, you see that we get just the Hamiltonian in this way. We can also introduce a characteristic polynomial of the Lux matrix in the usual way. And in the way similar to the Kalodger-Moser model, the equation that it is equal to 0 defines a spectral curve. Its properties can be found much in the same way as we did it for Kalodger-Moser model. In particular, it can be shown that the genus of this curve is equal to n. This curve gamma, again, it is a covering of elliptic curve, and we will see. We can, in fact, we can write this equation in explicit form because this determinant can be calculated using the fact that this Lux matrix is a product of diagonal matrix with these elements and this matrix which has the form of elliptic Cauchy matrix. The rational Cauchy matrix is a matrix with this matrix elements. And in the rational case, it's relatively easy to find its determinant and inverse matrix. It has elliptic generalization. The elliptic Cauchy matrix is matrix of the following form. Here we have, it depends on additional parameter lambda. And you see that if y is x plus eta, we obtain this matrix here. And determinant of this elliptic Cauchy matrix can be found. And the answer is of the following form. this is a problem for you to prove this formula. It can be done in the way which I explained before. Just divide everything by the right-hand side, for example, and consider this function as a function of one of the arguments, say x1. And you can see that this function is double periodic, and all possible singularities cancel. This means that this function does not depend on x1, some constant with respect to x1. However, the left-hand side is symmetric under the permutations of all arguments. So this means that this function doesn't depend on all arguments. So it is a constant. And this constant can be found by putting this argument to some value or expanding this function near some special point. It is not very complicated problem. The more difficult problem is to find matrix which is inverse to this elliptic Cauchy matrix, but this is also possible. You can find the answer in the literature. Using this formula for determinant of elliptic Cauchy matrix, we can calculate this determinant, because we should use, if we have a matrix, then such determinant, if say determinant of unity matrix plus some arbitrary matrix. This can be written in the following way: plus trace plus 1/2 plus diagonal minors 2 by 2. So this is summa par aj, ij, ij, jj, plus, in a similar way, sum of all diagonal minors of this matrix A. But each such minor is a matrix of the same form. It's some elliptic Cauchy matrix, so its determinant this can be calculated explicitly, and these arguments lead to the following result. This is a polynomial in Z of degree n, and the coefficients can be calculated explicitly. These coefficients are conserved quantities, and the formula for them is as follows. sum over all sets of k indices distinct. All of them are distinct. And in terms of momenta, this integral of motion has the following form. Sum over all subsets of the set of indices from 1 to n with k elements. In fact, we're already familiar with these expressions because in the rational case it has similar form, but instead of sigma function we have just sigma of x, we have just x. In particular, the highest one, in, is proportional with some constant proportional to exponent of sum of all momenta. In a similar way, we can introduce integrals with negative indices. And they are given by a similar formula with plus minus eta here. So looking on this equation, we can find some properties of the spectral curve. For example, when lambda goes to 0, z, again, this is a covering over elliptic curve, and this is a point lambda equals to 0, and there are n sheets above this point. And one of them, for example, the upper sheet, corresponds to z equals to infinity. But unlike the elliptic Calogero-Moser model, where all these points were infinite points at infinity, here, in this case, only one of them lies at infinity, and the other ones are finite. So among n roots of this equation at lambda equals to 0, we have only one infinite root. The other n minus 1 roots are finite. So this is one special point. So the point on the curve is a pair of two arguments which are connected by these equations. So one special point is point at infinity. There is another special point obtained when lambda equals to n eta, the last term in this sum. You can see that in this case, this last term, when k equals n, vanishes at this point. So the equation has a zero root. So there is another special point, lambda equals to n eta. There are n points above it, and this point, when z equals to 0, is one of the points of the curve lying above this point. All other solutions of this equation are some finite numbers. In this way, we can fix two special distinguished points on the curve, this one and this one. Unlike the Kalogero-Moser model, where only one point was distinguished, here we have two. And this has some interpretation in when we consider this Rusinard-Schneider dynamics as dynamics of singularities of elliptic solutions to Toda lattice equation. And according to Kricevier's construction of algebra geometric solutions to nonlinear equations, such solutions are associated with an algebraic curve with some marked points on it. And for Toda, you should take a Riemann surface of some genus G with two distinguished points. One of them usually called infinity, and another one is 0. So these points are exactly what we have here. I will not discuss these other properties of the spectral curve and the calculation of genus. You can do it yourself. And now I would like to make some general remark. So let us consider such table. So we have discussed models of different types, Kalogero-Moser models, Rusinard-Schneider, and all of them have Hamiltonian. All of them are Hamiltonian systems, and the Hamiltonian, they have some Hamiltonian depending on momenta and coordinates. There are many of them, n. And let us see what kind of dependence on momenta and coordinates have these models which we discussed. This dependence can be of three types: rational, trigonometric, or elliptic, most general. So here we, in this direction, will be coordinates, and this direction, momenta. So rational, trigonometric, and elliptic. here rational, trigonometric, and elliptic. In this square, we have rational Calogero-Moser model, where dependence on momenta is rational, moreover, even polynomial. It was sum of pi I squared. Here we have trigonometric Calogero-Moser model, because the dependence on momenta is the same, but the interaction potential is already a trigonometric function. Here we have most general case, elliptic Calogero-Moser model. So the kinetic part of the Hamiltonian is still sum over squares of momenta, but the interaction potential is elliptic function. Now, let us go further. In the trigonometric dependence on, so this is rational plus potential part, and trigonometric, so this is Calogero-Moser, this is Rosenard-Schneider. It is exponent of momenta, or if we take linear combination of h plus and h minus, here we obtain some trigonometric function, sinus or cosinus. So this is a function with just one period in complex plane. We call such functions trigonometric. But dependence on coordinates may be of different types. Maybe rational, trigonometric, or elliptic, which we just discussed. Now, what about duality transformations? These types of models are related by duality transformations. For example, the rational Calogero-Moser model is self-dual. And it can be shown also that trigonometric Rosenard-Schneider model is also self-dual. And these two models are related by duality transformation. We will not discuss it in detail. You can, if you are interested in this, you can do it yourself. And the question, natural question, is what is dual, for example, to elliptic Calogero-Moser model? So what should be here in this square? So in this line, we have some hypothetical models with elliptic dependence on momentum. And some progress in this direction was done quite recently, a few years ago, when some candidate for this double elliptic model was suggested. So these models are called DELL, which means double elliptic. So the dependence on of momenta and coordinates are both elliptic. And in general case, they are elliptic functions with different elliptic model. I mean, what is elliptic models? If we have fundamental domain, for example, this is one, this is we have periods omega 2, omega 1, and their ratio are called tau. And this tau is called elliptic model. Elliptic curves with different tau are not isomorphic. There is no conformal isomorphism between them. So they are essentially different curves. And here we have dependence on coordinates with some tau elliptic model and dependence elliptic momenta, some other parameter which is called omega. This was suggested, this double elliptic model was suggested a few years ago in the paper by Karateev and Shakirov. And they suggested it in quantum, already quantized, in quantized form, so the Hamiltonians were operators. We will speak about classical limit. So this is I don't remember year, for probably a few years ago.
2019.
19?
Yes, it's right.
2019. It's not so easy to explain their motivation. You will see that the result has a rather complicated form, and it is not looking on it. It is not clear how it is motivated. But their motivation came from string theory, something like that. But the result is the following. Consider, and I will show it in some other form, not an original form of Karateev-Shakirov, but in the form which was elaborated by Grekov and Zotov. Consider such function, which is called O, capital O. It depends on two parameters, Z and lambda, like what we had in the Rogenas-Schneider model. And it is given by the following series. So these are, the sum is over all integer, n integer numbers. Instead of Weierstrass functions, in this case, it's more convenient to use theta functions, especially this theta1 function, which is given by the following series. This is an odd function, having simple zero at the origin. And this, I forgot the most important thing, the parameter tau. These functions have tau as elliptic model. So x, I, and pi are coordinates and momenta, having canonical Poisson brackets. Tau and omega are elliptic modulus, so these theta functions depend on tau, and this factor depends on omega. When omega goes to infinity, it can be shown that just another step. So consider it as a series with some coefficients. Some coefficients expanded in a Laurent series in Z, and call the coefficients OK. And then the Hamiltonians are defined in the following way. So you should consider ratio of two such coefficients, and the hypothesis, not proven yet, is that all of them commute, Poisson commute. And after quantization, when this operator becomes a shift, instead of number, this guy becomes operator of the form some derivative over x, the exponent of it is a shift. Here you probably have eta. And in quantum case, the statement that they commute is a hypothesis verified numerically for some set of these Hamiltonians. So this is the open question. Any proof is missing. But this is important that you should take a ratio of two coefficients, and in fact, it doesn't matter which ones. So this one is not necessarily zeroth coefficient, can be taken arbitrarily. Then these Hamiltonians will still commute. Again, conjecturally. this generating function of this Hamiltonians can be, this is a result of Grekov and Zotov, can be written as the following determinant. Where this L So you should take Rusinar's Schneider Lux matrix depending on eta, and consider this infinite sum, and case term has k eta as a parameter. So this matrix has the following elements. It can be shown that when omega tends to I infinity, this construction gives the elliptic Rusinard-Schneider model. So this equation of L which defines some curve, the spectral curve. And this spectral curve, when omega tends to infinity, becomes the equation for the spectral curve of the elliptic Rusinard-Schneider model. So using this construction, it is possible to see what happens in these squares. So these are some models with elliptic dependence of momenta and rational dependence on coordinates. You can find some examples in the paper by Mironov and Moroz, rather recent paper about, don't remember, maybe 22. So if you get interested, this you can see this literature. Another question is about duality transformation. It seems that this Karateev-Shakirov model, it is double elliptic, but it is not self-dual like these models. Self-dual. When dependence on coordinate momenta are of the same type, rational, trigonometric, here elliptic, and we could expect that these models are self-dual, but this is not the case. So there are, in the literature, there are attempts to suggest some models which would be self-dual with elliptic dependence on coordinates and momenta. But some progress was made only for systems of two particles. When number of particles is arbitrary, it seems that there are no results. Okay. Now we will discuss some model which was suggested 2 years ago, and it is some strange deformation of the Rosenars-Schneider model, and connected with it in some strange way. Let me show you equations of motion for this model. It exists in all cases, rational, trigonometric, and elliptic, and we will discuss from the very beginning, discuss the most general elliptic case. This expression is what we had in the Rosenars-Schneider model. It was equal to 0 in that case. But now there is some additional term. Where I is given by the following product. you see that this additional term is of very strange form. When g is equal to 0, we have the non-deformed original Rosenau-Schneider model, but in fact, you see that the value of g is not important, because by rescaling the time, something like this, you can always fix g equal to 1, for example. But for us, it will be more convenient to fix it to be sigma of 2 eta. Again, there are two possibilities. G may be real or maybe imaginary. Then this just means that the time would be either real or imaginary. Algebraically, this does not matter. This model appears to be integrable, so it has enough number of conserved quantities, which can be found explicitly, and I will show them after some time. But this model most likely is not Hamiltonian. In contrast to the Rosenau-Schneider model, it is probably not Hamiltonian. One integral of motion can be found very easily. Just sum all these equations over I. Then we have xi sum of second derivatives. This term cancel, because this expression here is, you will see that it's easy to see that it cancels. But what about this one? One can prove that the following identity holds. So then, after summation over I, this additional term cancels. And we have this equation, which means that A1, which is equal to sum of all velocities, is integral of motion. This identity can be proven if we notice that this expression is a sum of residues of some elliptic function. This is a good exercise to find this elliptic function. In fact, it is something like this. Something like you see that this function is elliptic in x because here we have 2 eta minus eta, so eta, and here we also have eta. So this is double periodic. And it is easy to find the poles are at the points xi minus eta and x equal to xi. N poles of this form and n poles of this form. And it's easy to find the residues. If you do this, you get exactly this relation, that this is the sum of these residues, and as a sum of all residues of elliptic function in fundamental domain, it must be 0. In fact, this model, after some time, we will obtain these equations of motion as equations of motion for poles of elliptic solutions to some version of the Toda lattice. But at this time, we should I would like to explain how this equations of motion can be obtained starting from the usual non-deformed Rosenard-Schneider model. In fact, they are somehow contained in this model is, in some sense, is contained in the non-deformed model. Namely, consider the following configuration. 2n particles, 2n Rosenard-Schneider particles, which form pairs such that x I plus 1 minus x 2 x2i minus x2 2i minus 1 is equal to eta. So they are in pairs. And this distance between them is eta. This is x1, x2. And suppose that these pairs move as a whole. So this distance between particles in each pair remains the same, equal to eta. So they move as whole things. Of course, such configuration is not conserved under Hamiltonian flows. For example, it is not conserved under the Hamiltonian flow H plus plus H minus. This configuration is immediately destroyed under this flow. However, if we consider another flow, H plus minus H minus, then it can be shown that this configuration is preserved by this flow. So this is a bad flow, this is a good flow. Moreover, it can be shown that for arbitrary, for higher Hamiltonians, hk plus h minus k, these higher Hamiltonians destroy this configuration, but hk minus h minus k preserves it. So we can restrict the space of the set of flows to only to the good flows. So first we restrict our phase space, which is 4n-dimensional, to 2n-dimensional phase space corresponding to such configuration where the distance between particles in each pair is frozen. It's important that this distance is equal exactly eta, because eta is a distinguished scale in this model, scale in space. If we choose this distance in any other way, some other, put it equal to some other value, then everything destroys. Eta is important because it enters in the Hamiltonian. I'm not sure that it makes sense to show you the proof because it's rather complicated. It will be in written lecture notes, which will appear on the site. But now I will just probably say only some words about this. So consider the flow under this Hamiltonian. Let us denote it h bar. Then the velocities are as follows. These are velocities for particles with odd numbers and with even numbers. It will be the following. If we impose the constraint that the distance between even and odd particle in each pair is equal to eta, then this term vanishes, because here we will have one multiplier equal to 0 under this constraint. And this term vanishes. So we are left with only these terms, and what we should require that these velocities are equal in order to preserve this constraint. This gives some constraint on the momentum, because you should require that these two are the same. And this gives the following relation for momentum of even and odd particles. Where alpha I is where x capital are coordinates of the pairs. Originally we had two n particles, but now we have only n pairs, and this x capital are coordinates of this particle. So we have restricted our original phase space to smaller space with coordinates p capital and x capital. Here we have 4n coordinates, and here there are 2n coordinates. And now the dynamics, these good flows define some dynamics in this space. It is a relatively long calculation to show that this dynamics is exactly what is written here.
We have some conserved flows that are not Hamiltonians.
Mm-hmm.
So this system has conserved variables, but isn't Hamiltonian.
Yes. But we originally, in the original Rosenard-Schneider model, the dynamics was defined by Hamiltonian equations. So it was a Hamiltonian flow. And here this dynamics is defined from the Ruijsenaars-Schneider model of two n particles. If you restrict it to this subspace, you get dynamics already inside this space, which is not Hamiltonian.
You said that we will introduce this dynamics by the Hamiltonian equation using one of those flows, like H plus minus H minus. So why this is not Hamiltonian? Because we don't have the second Hamiltonian equation, or what?
It's a good question. The situation is not completely clear for me. It turns out that if you restrict Hamiltonian flow to some subspace, it fails to be Hamiltonian. So I don't know. Okay, we have just few minutes, and I think it's not time to discuss commutation representation for this model. We'll do this next lecture. But now I will just say some words about it without any details. These equations of motion can be obtained as a condition of commutation of some matrices, like it was in Ruijsenaars-Schneider model. So, but however, the Lax representation does not exist for this case. Instead, you have what is called Monakov's triple representation. It has the following form. For Lax representation, this was 0. But now it's not 0. It is some matrix R. You may ask what, or it can be also written in some different form. Denote this matrix by L. So L was, it depends on lambda. And this L depends on k and lambda, and it is L of lambda minus ki. Then, in terms of this this letter L, the Monakov's triple representation looks like this, where M minus and M plus are some matrices, which I will show them explicitly next time. In Lax representation, they are equal. And we can conclude that the evolution is isospectral. Now it is not isospectral. So the eigenvalues don't conserve. However, it can be, from this Monakovsky representation, it can be shown that that determinant of this matrix L is conserved. Only determinant, not eigenvalues separately. This is true in the case when this matrix R is traceless. This will be just our case for this model. It's easy to show. Easy to show. Just find time derivative of this determinant. But this is just trace R according to the Monakov's triple representation, and this is 0. This gives us a large set of independent integrals of motion. In fact, this determinant can be found explicitly, and this is a Laurent polynomial in Z, and each coefficients, the coefficients are integrals of motion, and they can be found explicitly. It's a more complicated calculation than in the Rusinat-Schneider model, but next time I will show you some details. Okay, so what? So we will discuss this, and after that, next time we will start to discuss Calogero-Moser-like systems with internal degrees of freedom. Then, when each particle is not just a scalar particle, but has some internal degrees of freedom, like spin. These models are called spin models, and these degrees of freedom are some vectors in space associated, in a linear space associated with each particle. And there are also Rusinat-Schneider models. They are generalizations to models with internal degrees of freedom. This is our program for next time, and after that we will start to we will discuss nonlinear integrable equations like Kadamtsov-Petriashvili, Toda, and we'll study how to obtain all these integrable many body models like Calogero-Moser and Rusinat-Schneider from dynamics of poles of solutions to equations of Kp and Toda type. Okay, today it's all.